Good morning, students. This is Dr. Baljeet Kaur Hundal from Government Polytechnic College for Girls, Patiala, giving you a lecture on the topic metallurgy of steel. Now, under this topic, we will be discussing the various contents. First, I will be discussing what is iron, what are the ores of iron, and then the varieties of iron. Under the varieties of iron, we will be discussing what is steel. Then in steel, we will be discussing about the types of steel also. Then we would be discussing about the manufacture of steel. The manufacture of steel will be started by two processes, the open hearth process. Then later on we would be discussing about the advantages of open hearth process. Then I would discuss the LD process for manufacture of steel and the disadvantages of LD process. Later on we will be discussing about the various types of steel. After discussing the manufacture, we will be discussing the types of steel, and then we would be studying about the heat treatment of various steels. So, let us start with our lecture. Now, what is iron? Iron, as we know, it is found in the earth's crust and it is the most abundant element that is present, and we have various ores of iron. The first ore of iron is hematite. Just see, this is hematite. Its formula is Fe2O3. The next ore is magnetite. Magnetite is Fe3O4. Then another ore is limonite. Limonite is Fe2O3, 3H2O. In limonite, we have 3 molecules of water also, water of crystallization also present. Then another ore of iron is siderite. Siderite is a carbonate. It is Fe2CO3. Then we have iron pyrites, that is FeS2. So, these are the various ores of iron. So, the various ores of iron are, let us revise again, hematite, magnetite, limonite, siderite and iron pyrites. Now, the next thing is what are the varieties of iron that we obtain. After the extraction of iron from ore, we have various varieties of iron. The first type of iron is cast iron. This iron is also known as pig iron, and it contains large amount of carbon. The carbon in this type of iron is 2.5% carbon, and we have small amounts of other elements also like manganese, silicon, sulfur and phosphorus present along with iron, and this is the most impure form of carbon of iron. So, just remember cast iron, it is also known as pig iron. The percentage of carbon is more in it and it is the most impure form of carbon. The next type of iron is wrought iron. Wrought iron is the purest form of iron, purest in the sense that in this iron the carbon content is lowest. It is just 0.2 to 0.5%. This iron is malleable, ductile and soft. So, wrought iron is the purest form of iron and cast iron is the impurest form of iron. So, these are the two major forms of iron. The next form of iron that we are studying, that will be the steel. Steel contains 0.1 to 1.5% of carbon besides iron, and it is an alloy. Basically, steel is an alloy of iron and it contains traces of manganese, chromium, nickel, phosphorus and sulfur. So, we have 3 types of iron: cast iron, which has 2 to 5% of carbon. Then we have wrought iron, where the carbon percentage is very less, and so it is malleable, ductile and soft. And then we have the steel that has carbon content in between that of cast iron and wrought iron. Now, I have used the word alloy. So, let me tell you what is an alloy first. Alloy is a homogeneous mixture of two or more metals and non-metals. So, what is an alloy? It is a homogeneous mixture of two or more metals and non-metals. And we have two types of alloys. First is the ferrous alloy and the second one is the non-ferrous alloys. As the name indicates, ferrous alloys are those alloys which contain iron as the main constituent. They will have iron. Ferrous word is coming from iron, so that means ferrous alloy contains iron, and non-ferrous alloys do not contain iron as one of the main constituents. They do not have iron. So, the examples of ferrous alloy is Invar, steel, alnico. And the examples of non-ferrous alloys are your gunmetal, German silver, which do not contain brass. These do not contain any amount of iron in them, so they are non-ferrous alloys. So, remember that steel is a ferrous alloy. Now, we will be discussing what is steel. Steel is an alloy of iron containing 0.1 to 1.5% of carbon and traces of manganese, chromium, nickel, phosphorus and arsenic. And as the percentage of carbon increases up to 1.5%, the steel becomes harder and tougher, because the carbon gets chemically combined with iron to form iron carbide. So, what is steel? Steel is an alloy of iron and it contains 0.1 to 1.5% of carbon along with traces of manganese, chromium, nickel, phosphorus and arsenic. And as the percentage of carbon increases up to 1.5%, the steel becomes harder and tougher, because carbon will react with steel iron of the steel to form iron carbide. So, this is what is steel. Now, we will be studying about the types of steel. We are seeing that the percentage of carbon in steel is in between that of cast iron and wrought iron. So, steel can be made either by increasing the percentage of carbon in wrought iron or by decreasing the carbon content of cast iron, or by mixing wrought iron and cast iron in a fixed proportion. We have seen I am just rewinding the slides, that cast iron has 2 to 5% of carbon, wrought iron has 0.2 to 0.5 and steel has 0.1 to 1.5. So, this is in between that of cast iron and wrought iron. So, it can be manufactured by either increasing the percentage of carbon in wrought iron or by decreasing the carbon of cast iron, or by mixing the wrought iron and the cast iron in a fixed proportion. Now, let us see the various types of steel. Depending upon the percentage of carbon, steel has been classified as mild steel, medium steel and hard steel. Again I am saying, I will later on also tell you that we have a very hard steel also. Mild steel has less carbon, medium steel has carbon in between and hard steel has more of carbon. So, let us see them. Mild steel contains 0.05 to 2%, note it down. It contains 0.05 to 2% carbon. It is malleable and ductile, and it is used to prepare sheets and wires. It is suitable for welding, and it has low tensile strength. Its tensile strength is quite low. So, this type of steel is used for making wires, rods, ship plates, etc. So, mild steel has very less percentage of carbon, and that is why it is soft. It is malleable and it is ductile, and it can be easily welded. You know the meaning of welding? To join two metal parts with the help of an electric arc. So, mild steel can easily be welded. Now, the next type of steel, it is medium steel. Medium steel contains 0.2 to 0.6% of carbon. It is harder than mild steel because the carbon content has increased, therefore, it is harder than mild steel. It is fairly good for welding, you can weld it easily, and it can be hardened by heat treatments. Later on at the end of the lecture, I will be discussing about heat treatments. This steel can be hardened by heat treatments, and it is used for constructing rails, wheels and bridges. So, this is the medium steel. Then the third type of steel is hard steel. Hard steel contains 0.6 to 1.5% carbon. It is more than mild steel and medium steel. This can be welded with great care. In this case, welding is not easy. It has to be welded with care. It is very hard, and its hardness can be increased by heat treatment. It is already hard because of more carbon, and its hardness can be increased by heat treatment. And this steel is used for making machines, dies, screws, cushions, springs, etc. So, this is hard steel. I was telling earlier also, we have still a very hard steel also. In this content, the carbon content is still higher, it is 0.7 to 1.5%. This steel is not weldable, and it can be hardened to a large extent by heat treatment. It can be hardened, it is quite strong, its strength is more, and therefore, it is used for making railway rails, rock drills. Rock drills, you understand? The drills that are used for drilling rocks. Then chisels, something that is used to chisel out something, and knives. They are made up of very hard steel. So, we have three types of, or we can say 4 types of steel. Mild steel, where the carbon content is very less. Then we have medium steel, carbon content is in between, it is harder than mild steel. Then we have hard steel, which contains still more percentage of carbon, it is more hard. And then we have very hard steel, where the carbon content is a little bit more than the hard steel, and this can be used for making railways, rails, rock drills, chisels and knives. So, this is about the various types of steel. So, we have seen that steel consists mainly of iron and carbon, and the carbon percentage is between those of cast iron and wrought iron. Now, we will be discussing about the manufacture of steel. We have seen the various type of steels, we use steel every day in our life. We will see what are the methods of manufacture of steel. We will be discussing two methods of manufacture of steel that are in your syllabus. The first is the open hearth process and the second is the LD process. First we will be discussing about the open hearth process. The open hearth process was invented by Sir William Siemens. This method is also known as, just note it down, Siemens-Martin process. I haven't mentioned it here. It is also known as Siemens after the name of its inventor. This is also known as Siemens-Martin process, and this is a modern method of manufacturing steel, and it is an economical method to manufacture steel. Now first let us see the open hearth furnace in which the steel is prepared. This is a open hearth furnace. Here we are having a brickwork. This is a brickwork. This is a second checker work of bricks. This is also brickwork. From here various gases like the producer gas and the air, they are made to enter inside, as you are seeing here. This is the hearth. Hearth is the place on which the charge is placed. What is charge? Charge is the substances that are being placed from which we are extracting steel, that is known as the hearth, and from here the gases which are hot make their exit. I am having another diagram also, I will show you. This is a colored one. This is the diagram, a refined diagram. This is a checker work, the same checker work that you were seeing here. It is the same checker work. From point A, the producer gas and the air, they are entering inside. They are still moving through these pipes. Here they are coming. This is the hearth. D is the hearth, and C is your charge. Charge is the substance that is being placed over here, the ore and everything else. And from point E, the spent gases are moving out. So this is basically what a open hearth furnace looks like. Okay, we have two checker work of bricks. One is this checker work, this is the second checker work of bricks, and this is the hearth over where the charge is being placed. Now let us see how steel will be made. Now the chart that we take over here is pig iron mixed with 25 to 40% of the weight of scrap iron, low grade iron and hematite. Scrap iron is any iron that we get, the rough iron that we get in the market. Low grade iron, even the things that are already consumed, they can also be used. And hematite, that is the ore of iron. The scrap iron, low grade iron and iron oxide, they are mixed together and they are placed in this hearth over here. The bed of the furnace is either basic consisting of lime or magnesia or acidic consisting of silica. This is the bed, this bed D. It can be either basic or acidic. It will be basic, made up of lime or magnesia, and acidic, when it is acidic it will be lined with silica, depending upon the type of impurities. If we have acidic impurities, we use a basic lining. If we have basic impurities, we use a acidic lining. Now let us see further. Now this mixture burns over the hearth of furnace through a checker work of bricks. From here heat is coming. Heat is coming by producer gas and air. This is being heated and then heat is coming here. the mixture burns over the hearth of furnace and produces a very high temperature of about 1920 Kelvin. At the hearth or at this place, the temperature will be approximately 1900 Kelvin. Just see the temperature. It is, that means it is very high, around 1900 Kelvin. This is a very large temperature. These hot gases make their exit through the second checkerwork of bricks. It exits through this checkerwork of bricks. From here it is moving out. Now, when the second checkerwork gets sufficiently heated up and the first one gets cooled, the direction of passage of preheated producer gas and air is reversed. What do we mean by it? The hot gases are coming from here, they are passing over the hearth, they are melting down the charge and they are moving into the second checkerwork. When these gases, hot gases will move toward the second checkerwork, they will make this checkerwork hot. So, when this checkerwork becomes hot, its temperature reaches above 2000 Kelvin. What we do? We stop the passage of these gases from here and it is reversed. So, this hot temperature will start going towards this side and this will start cooling. Now, this way the flow will take place. So, this flow is kept changed every time. First we flow the gases from this side, later on when this also gets heated up, we make the flow from this side, again this will get heated up, again we will convert the size, change the sides. When this will get heated up, we will again change the direction of the gases. So, that means this process is economical and is based on regenerative principle of heat economy. So, we are saving heat, that is the basic idea, that we are saving heat, we are saving the gases. Now, let us see actually what are the reactions that are taking place. Due to the burning of producer gas, high temperature is obtained. The temperature becomes very high. The charge melts and the impurities like carbon, sulfur and silicon and phosphorus get oxidized by hematite as shown below. Carbon will react with Fe2O3 to form iron and carbon monoxide. Sulfur will react with Fe2O3, it will form iron and sulfur dioxide. Then silicon will form iron and silicon oxide SiO2. Phosphorus and Fe2O3 will react to form Fe plus P2O5. This is phosphorus pentaoxide. So, we are seeing that the impurities of carbon, sulfur, silicon and phosphorus, they are being converted into their oxides and iron is obtained. Now, these two, carbon monoxide and sulfur dioxide, they are gases, they will escape out. They are hot gases, they will escape out. We are left with silicon oxide and phosphorus pentoxide. Let us see what happens to them. The silicon oxide SiO2, what happens? We have added lime also to the charge. This is also calcium carbonate. It is converted into lime, calcium oxide plus carbon dioxide. The calcium oxide, that is lime, reacts with silicon oxide to form calcium silicate, and calcium oxide reacts also with phosphorus pentoxide to form calcium phosphate. These two will form the slag, and the carbon is removed as carbon monoxide and sulfur as sulfur dioxide, as we had seen here. These two are gases and they can be easily removed. And the silicon oxide and the phosphorus pentoxide, they will form the slag. This slag can be removed. This process takes about 10 to 12 hours. The samples are taken from the earth time to time and they are tested for the carbon content. And when the required percentage of carbon is reached, that means from 0.5 to 1.5% carbon we get, then a calculated amount of spigallicene, this is spigallicene, remember the spelling, spigallicene, which is an alloy of iron, manganese and carbon. This is added to the iron and aluminium or ferrosilicon to get the steel of required quality. The molten steel and slag separate into two different layers. The upper layer of slag is removed and molten steel is poured into molds. I will just tell you in the diagram. Here in the earth, we will have two layers formed. One will be of the slag, upper layer, and the lower layer will be of the molten metal. The slag and the metal, they can be separated. Slag can be taken out and then metal can be taken out, that is steel, and this steel can be molded or it can be put into the, because this is molten steel, so it can be put into the molds that we require for molding. So, this is the open hearth process of making steel. Let us see the advantages. The waste scrap and low grade cast iron can be changed directly into steel. We are using even the inferior quality of iron for steel making in this process. Here the loss of iron is very less. This operation is slow and it is easy to control and get the steel of desired quality. And heating is done on the regenerative principle of heat economy, and the quality of steel is high and it is free from defects like blowholes, etc. So, these are the advantages of open hearth process. Just have a look at it again. The waste scrap and low grade cast iron can be changed into steel directly. There is no loss of iron. The operation is slow and it is easy to control, and heating is done on the regenerative principle of heat economy, and it is free from defects like blowholes. Now, let us see the next process, that is known as the Linz-Donawitz process. This is the latest development in steel making, and the name comes from the initials of two separate plants in Austria at Linz and Donawitz. So, that is why this is known as Linz-Donawitz process, or commonly we call it as LD process. In this case, 99% pure oxygen is used instead of air. In the open hearth process, we were using air, and in the LD process, we use 99% oxygen for melting the iron. And this process, and even for oxidation also of the impurities, we will be using oxygen over here. This process is presently used at Rourkela in India. Rourkela is famous for steel making, and this LD process is used at Rourkela. In this process, we use a furnace that is quite similar to the Bessemer converter. I am showing you the diagram of a Bessemer converter. This is the furnace over here. This is the top opening. This is the vessel. It is mounted on turnions. Turnions is, that means it can be tilted, turned out. But in a Bessemer converter, we have tire of air. Oxygen is coming from beneath. But in the LD process, I will show you. This is LD process. The oxygen is coming from here. This is the oxygen lance from where oxygen is coming. The vessel is the same. This is the converter. This is the furnace lining that is there. It is made up of steel, and then this is the oxygen lens, and this furnace can also be tilted. This is the straight position, this is the tilted position for pouring out the steel. Now let us see the process. LD converter is built with steel lined inside with magnesia. This is the furnace is made up of steel, it is lined inside with magnesia. It is mounted on turnions and can be tilted to any desired